the spin polarization, the spin lifetime, and the spin diffusion length. Now we can do, this was done at one temperature, 40 Kelvin. We can do this at many temperatures. And so if we do this for the spin polarization, we see that the spin polarization just decreases monotonically. And it decreases with this kind of law, which is called the Bloch law. So what happens is, as you increase temperature, you excite spin waves in the magnet, and the magnetization decreases. You essentially thermally excite the magnetization to move. And this equation describes that, and you see it just continuously goes down. But if you look at the spin lifetime, surprisingly enough, the spin lifetime goes up and then goes down. And so it really mimics what we see here. And in fact, so the spin lifetime gives us the spin diffusion length through this relationship here. And you see if you plug this in there, you can easily get this behavior. So now you say, oh, well, spin lifetime is non-monotonic. What's so interesting about this? Well, it's very unexpected, because in metals, we know how spin relaxation is supposed to work. Spin relaxation comes from something known as the Elliott-Jeffrett spin relaxation. And what it means is, as the electron moves through a material, every time when its momentum changes, there's a finite probability of flipping the spin. And so this means that the spin relaxation rate, which is the inverse of the spin lifetime, should be proportional to the electron relaxation rate, and therefore it should be proportional to the resistivity. We know what the resistivity does, it just goes down and then stays flat. So the spin lifetime should go up and stay flat, but it goes up and it goes down, so that's very unusual. But now if you look at this, and I'll just take like a couple of minutes to explain this, 2 minutes, and then I'm done. So if you look at this, the electron relaxation rate is of course due to many different processes. It can be due to phonon scattering, impurity scattering, and it can be also related due to scattering of the surface. And so similarly, the spin relaxation should be due to phonon scattering, impurity scattering, and surface scattering, but each of these scattering mechanisms may have a different probability for flipping the spin. All right? If you think about it in these terms, it's easy to see what's going on. So this is how the spin relaxation should be. We know what the phonon scattering does at high temperatures. It goes as 1 over T. So at high temperatures, spin relaxation is due to phonons. Impurity scattering is constant. And the surface scattering is actually, should be proportional to T. So at low temperatures, we see scattering due to the surface. And now what we can do is, we can fit this quantitatively, and what we see is that the probability for flipping a spin at the